This is further stats 2 from 2022. Let's just do it. So it's all about regression, this first question between tea yield and temperature, I guess. So of course we've got that, well, we predict that maybe these two things are positively correlated. The higher the temperature, maybe the more yield. And yeah, so we'll just set up that yield equals this gradient times the temperature plus this y-intercept, or the other way around. It doesn't really matter between these two, I guess. And yeah, we have this, so put in 20 degrees here, and we expect a yield of this here, which is good. He then produces this residual plot. So a residual is the difference between the predicted value that you'd get if you use the regression line to the actual value that was observed. And you just have to say something to that effect. Calculate the PMCC. So we've got a bunch of formulas in the formula book that will help us out here. This is the most obvious one, except we don't have the cross term for this S here. So that doesn't immediately work. But we do have this one as well in there. If you look a little bit deeper, all about finding the right things in the formula book when you can. This one seems particularly helpful because this R here, I think, well, the R here is what we're trying to find out, right? The R from the product moment correlation. Oops, I'm going the wrong way. The R from the product moment correlation coefficient is this R here. It's also this R here, but we have the residual sum of squares. It's this there. So we have that number there is equal to SYY, which is just this one here, into 1 minus R squared. And we can solve that for R squared. I'll save you time and just write it down, but we can all solve that, of course. It's positive because the two things are positively correlated, as we saw before with this gradient. Explain why the linear model might not be a good fit with reference to this. Well, that's not massively positive, so it's quite close to 0. You don't want to say it's low because, of course, if it was like minus 0.9, that's low, but it's very close to -1. So say it's close to 0. So that's quite weak correlation. Also, this residual plot. Now, if we cut the residual plot off here, these seem nice and random, and you want your residuals to be random to show linear correlation. But the moment the residuals start doing this, kind of after t equals 20, that's kind of showing that all the residuals between 20 and 21.5 are all negative, and then all of them above that are all positive in this kind of linear formation. The moment the residuals aren't acting completely randomly, that's a tip that it's probably not a great linear correlation. There's probably something else going on that's causing them to all be below it here and all above it here, and on your linear correlation or linear fit is not great. So if you see this kind of thing, it's great. If you see this kind of thing, not so great. Good. So this person collects some rainfall, which is different to what was going on up here, notice, and comes up with this, and concludes because this residual sum of squares is smaller, then therefore his relationship is better. It's a stronger relationship. Now, that seems like it's quite logical because, of course, the residual sum of squares is the difference between the, the, the predicted value and the actual value, and then you take it away and square it. And so the larger difference between the predicted and the actual value, the bigger the sum of squares will be. Except that's only in theory, right? Because he's measuring something completely different to what's over here. So imagine like all of the statistics were incredibly low, like 0.1 and stuff like that. And your residual was, a big residual was like 0.1 away from something. When you square that, you're going to have like a very small stat, and then you'll add 30 of them together, and you'll still have a very small stat. But it's possible that they were quite far away from what was actually going on. It's just all the numbers were very small, right? So when you're measuring two completely different things, you can't just take these numbers like for like, right? They depend on kind of the absolute size of the things that were being measured, which of course then you do all this dividing and stuff, and that will all balance out in the end when you get your final answer. But you can't just look at these two numbers because, yeah, when you're measuring completely different statistics, if one statistic has very small absolute values, the residual sum of squares is just naturally going to be small, even if there's not great correlation or fit. Anyway, question number 2 then. So just say something to that effect, I guess, in the previous question. A factory produces yellow and white boards. Got some statistics here from quite large samples. Find a 95% confidence interval. Just be aware that there's very little about confidence intervals given in the formula book. So those are the things that you need to be just knowing when you go into the exam. This will be the most useful one for us to use right away. We're just focusing on the yellow. This is the standard deviation, which we've got. This is just root n, which we've got. This is the mean, which we've got. And z is just the normal distribution with a 95%. And you can do that in a calculator if you want to. This is on page 121 of the textbook, by the way. Or you can use the tables for the normal distribution. Of course, it's a two-tailed because it's a confidence interval. So look for 0.025 and it'll be that one there. You're allowed to quote that without any evidence as to how you got it. You put those things in and you get your confidence interval right away. Now, we are claiming, or Jamie is claiming, that the population of yellow balls has a greater mean than the white, and we're going to test this. But first, it's asking us to specify the distribution of y bar minus w bar under the null hypothesis. Now, the null hypothesis is going to be that the means are the same. So the mean of this will be 0, because the null hypothesis says that the means are the same, and the same thing minus this alpha is 0. The variances, no matter what you do, take away or add, the variances always add. So the variance of this, of course, is 1.2 squared, because that's the standard deviation there, so we'll square it for the variance, plus this one as well squared, and we'll get our new normal distribution here. We can use a normal distribution, and this is this question here. The reason we can use a normal distribution is because these sample sizes are very large. And so the mean of a large sample by the CLT, the central limit theorem from FS1, means will always tend to a normal distribution. Because that CLT applies, that's something that we learned in FS1, so it's interesting that we earn a mark for remembering that. But yeah, that's why I can say that. And now it's actually asking us to pull off this hypothesis test. So obviously, we'll start with our H0 with the two means the same, and then H1 will be that this one is greater than this one, so this will be a one-tailed test, which will come in handy or relevance later. Look through the formula book. There's one particular page that has all the useful stuff on it for FS2, really. But this one here is what we're going to be talking about, because we're testing the difference between means. So it's this massive formula here. You kind of recognize it as soon as you see it as being the right one to use, I think. So just go grab it. You've got X bar is this, and Y bar will be that. Mu x minus mu y, again, this assumes the H naught, the null hypothesis. Mu x minus mu y is 0, according to the null hypothesis, because those two things are equal. Start get replaced with a 0. We have these two things, those are those two things, and we have the ends, those are those two things. And so we can get a test statistic out from here. We can just plug that all in and get this test statistic. We'll do the normal distribution, and again, just grab the normal table, or just use your calculator. It doesn't really matter. It's a one-tailed test, so we'll look for this one here, right? I think, yeah, this one here, next to this one. So, of course, that's the critical value. We're above the critical value, so we're in the critical region. And add some context, always add context in FS2 at the end of every question if you can. Say there is evidence that the mean of the yellow balls is larger than the mean of the white balls. Maybe say it more clearly than here, I was just running out of space. But anyway, that's the second question done. Our third question concerns two variables that are normally distributed here and here. And we're taking A independent observations from X, and then one from Y, and we're going to multiply that one by B. And we're going to say that has distribution this. Now, this is a great question because you actually get to do some proper maths. So, okay, well, W is, let's think about the expected value of W. It's just, and maybe I should have, well, it's not a show that question, so I think I get away with this. There's just A of these X statistics adding up. And so the expected value is just A lots of the expected value of each of those X's. And then, of course, we just have the expected value of BY as well. Except in expected values, you're allowed to just take this constant and move it out to the front. So we end up with that. And of course, we know the expected value of X is 5, because it's just the same as the mean. And the expected value of Y is 8. And so we end up with this here. And the expected value of W is this. So that's great. We have this here. And now variances we need to think about as well, which is slightly more difficult. But the variance of a bunch of X statistics added together is just the number A lots of them, times the variance of each one, which is different to what's going on over here. This is made very clear in chapter 4. When you add up lots of different statistics, the variance, you just take how many you've got and you put it down at the front like this. When you multiply a single statistic by a constant, that constant squares when you put it out the front. So that's the difference here, is we're adding up lots of different observations from the same thing. That just does this. When you're multiplying by a scale factor 1 observation, that's when you have this. We'll see that again later on in the paper. But anyway, we have all the variances. It's 2 squared as this one is 0.4 squared, this one is 0.1 squared, which makes all of this. I think I times everything by something here. What did I times it all by? Looks like I times it. No, I just divided by 0.16, I presume. That will probably be what I did there. And then, of course, I can just put that result into there. And I'll solve this for B in a calculator, of course. We'll get these two results. Now, there's nothing that tells me that B can't be 17.6. The problem is if you use 17.6 and you look at this equation here, you end up with A being a non-integer, and A is a sample of A independent observations. So that's just definitely a positive integer. So we can't end up using this, and maybe just explain that. We have to use B as 8, and when you use B as 8 and substitute it here, you get A as that, and that'll be our answer to this question here done. So question 4 then, we've got some stuff about resting heart rates before an exercise program and after, and this doctor believes that the exercise program has brought these resting heart rates down. We're going to do a hypothesis test to test this. So, okay, first let's write down our hypotheses. So H0 will be that the differences, the mean of the differences will be 0. We're going to work out all the differences, and if there's no difference before or after, really, then we're expecting some to be positive, some to be negative, and the mean to be 0. Of course, H1 will be that the mean is greater than 0. I've gone for greater than because I'm going to do the before minus the after. And of course, if these have decreased, as the doctor thinks, that means the difference will be positive, right? So that means the mu of the difference will be greater than 0 will be H1. So let's work out all the differences then. We've got all these. Just by doing some taking away, we get all this. This looks like a bit like an outlier, but they never ask about it, so it doesn't really matter. Of course, we can look in the formula book here, and this looks appropriate. Test for variance and mean when sigma is not known, or sigma is not known, and it's a test for the mean, so that's good. This catches my eye, talking about matched pairs, and we've clearly got pairs of data here, so that's kind of my cue for knowing that this is the one to use when we've got differences going on. So, okay, what do we need here? Well, x bar is just d bar. We can work out d bar quite easily just by adding all those up and dividing by 7. We need this estimator for sigma, and we can again use the formula book here. This is the one that they give us, and I actually just use this. If you prefer to, you could use this. Of course, this isn't given the formula book, so you'd have to know this, but this is really useful and does come up a lot in other papers. So maybe I would highly recommend you actually go in knowing this because it can be more useful. But in this case, I just used this. I just did 2 minus 4 all squared plus 3 minus 4 all squared and so on, and then just divided everything by 7 minus 1, which is 6. And I got this, which I then square rooted for this. And I think we have everything to go, ready to go for our test statistic here. We've got d bar is 4, mu is 0 according to the null hypothesis, s is this, and root n is just root 7. So we can calculate that. It's going to be this. And then we can look at our t distribution. We're going to do t degrees of freedom 6, because n is 7, 7 minus 1 is 6. It's a 5% test. It's, of course, one-tailed. So that's going to be this statistic here, I think. That will be our critical value. And then when we can just compare that this one is indeed greater than that one. So we're in the critical region. We're going to reject H0, and then again, just slam in as much context as you can. There's evidence to support the doctor's belief that blah, 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 and pick up that last mark. Set an assumption about the resting heart rates. Now, it's critical to use the word difference here because we tested the differences, didn't we? That was what we got this and this from. So it's not enough to just say that stuff is normally distributed. You have to say that the differences are normally distributed. Differences in heart rates are normally distributed. These numbers here, and because those are the things that we actually tested based on this idea here, which was this. So that's cool. Good. Question number 5 then. So we've got air pollutants in 2 places. This is some information about A. For B, we've just got that there are 9 samples and no more information. They've got a test hypothesis that the variances are the same or that they're not the same under 2%. State a necessary assumption. Well, again, just like we said before, let's say that they need to follow a normal distribution. They need to be normally distributed. That's always the go-to response to those questions, I think. Anyway, given that the assumption in part A holds, find the set of values SB squared that would lead to the null hypothesis being rejected. So when we do this, we can look here. We've got a random sample of n observations from site A and another one from site B, and we're going to test our 2 sample or our estimators, sorry, for the variance, which is going to be this one and the one that they're talking about here. So this is clearly a good one to use. We're going to use the F distribution. The nice thing about the F distribution is, this question says a set of values for SB. So that suggests that we're going to get more than one answer. And the nice thing about the F distribution, which is also the good hint that this is the one to use here, I'm using 0.01 here, by the way, because 2%, it's going to be, we're going to do a 2-tailed one because it's, of course, this. So we're down to 1% here. But when you're doing an F test, you can put either the X's on top here and the Y's on bottom, which would lead to the number of X's here, number of Y's there. Or you could go the other way around. And now, when we do nx minus 1, n minus 1, we get 12 here and 8 here. But you notice in your table, you could either go for 12 and then find 8 for this value, or you could go for 8 and then find 12 for this value. So there are actually 2 key statistics we can take from this table, and we can set up this stuff both ways around. By the way, this stuff doesn't really matter, because in the null hypothesis, those 2 things are equal. So when you put them in here, they'll just cancel out. So essentially, we've just got this divided by this towards the F test. So, okay, we can set up, if we're looking at this one, that means we put 12 first, That's V1. We've put that one first. So the x's come first. And so this one here comes first. We've got this one divided by SB squared. And that refers to this number here. So that's that one. And then for this number here, we've got it the other way around. We've put the 8's first. The 8's refer to site B. So we put the B's first, which means the B's come on top, and then the A's on bottom, and we set up this here. I've gone for greater than or less than because, of course, greater than, because we need to be, we're rejecting the null hypothesis. So we need to be in the critical region for both of those. So we need to be bigger than the values, the critical values from each table. So okay, we're bigger than both. Let's cross multiply here and divide by this. We get this, which is of course this, and likewise here we're going to just multiply that across. We get this, and those would be our two results. I don't think there's any better way for me to write that down. I'll just leave it like that. Find a 99% confidence interval for the variance. Again, I mentioned it before, but confidence intervals don't have very much stuff. There's not very much to help you in the formula book for them. So you do need to go in knowing your results for confidence intervals because there is just nothing in the formula book about them. So this is the one that we use if we're confidence intervaling a variance. It's on page 143 if you want to look at more stuff about it. We're just using site A now, so this will be 13 minus 1 is 12. We have this statistic here as that one. We look in the chi-squared table, and we're doing a confidence interval, so we need both the lower and the upper, of course. 99% means that we need to halve that down, or halve the 1% left over down to 0.05. And we're going to be looking at this value up here and this one all the way over there for 12, of course, because you've got n minus 1 is 12. So it's going to be this value and this one all the way over here. And of course, now we can simply say that we can take this value and divide by that one first, putting in 12 here and s squared from here, and we get this as our upper, as it turns out. And when we divide by this one instead, we'll get our lower, and then we can just write it out like this. They wrote it like this in the answer in the mark scheme I noticed. I think I'd get full marks for this, which is what I wrote, because that's just how you usually write confidence intervals. But just worth bearing in mind that that's how they wrote it, so maybe that's how you should write it as well. Excellent. So we enter this like 3 really nice questions at the end of this, that just involve a lot of really nice maths. Anyway, Korhan and apologies if I this person and Louise challenge each other to find the best estimator they can for the mean mu. This sounds like something me and Mr. Winfield would do in our downtime. Anyway, Korhan's got this estimator here, Louise has got this one here. Show that they're unbiased estimators. So for an unbiased estimator, or something like an unbiased estimator T, estimating something theta, the expected value of T should be equal to theta. That's for an unbiased estimator. So we're estimating mu, so we want E of K and E of L to be equal to mu. So let's work them out. Let's work out E of K. So just firstly, K is just, let's just unpick this a little bit. When R is 1, this is 1 as well, so we get 1 lot of x1. When R is 2, we get 2 lots of x2. R is 3, 3 lots of x3, and so on up to n. So that's K. Let's work out the expected value. Now, of course, this is just a constant, so it can come out before the E, and it doesn't do anything because we're just doing expected value, so it doesn't square anything like that. And now we've got all of these. Now we can do the expected values of all of these separately, like this. This is a show that question, so we want to just try and write down all of our working as we do this. Of course, these are now also constants, so they can all come out to the front as well. We end up with this. And now E of x1 is just the expected value from the variable x, which is the mean mu. So we can replace all of these with mu's, and we end up with this. And now we can just say, well, the mu's can be factorized out here to leave us with this. And again, it's to show that question. You might just immediately know that this is n into n plus 1 over 2, because of course it is. But it's show that, so maybe just doing this isn't enough. This is what I originally did, as I just wrote it straight down, cancelled all of this, and I immediately ended up with mu. But to be honest, what you should probably do, since this is a show that, is just go back to here for a second and note from the formula booklet that you have this formula for the sum of arithmetic series. I think this is just regular A-level maths, isn't it? I can't remember. And maybe just write this formula down to say that's how I'm getting that this result is going to be this. I actually use this result just because I never use it, so it just seemed like quite a fun result to use to just immediately get here. But anyway, so A is 1 and L is the last term n, and you just end up with this. This all just cancels and you get mu. So good. E of K is mu, which is what we wanted for an unbiased estimator. We'll do the same thing for L, and again, being as clear as you can, The expected value is this. We can split this expected value here and here. And then, of course, once we've done that, we can take the third out and this 1 over this out, because those are just constants. And now the expected value of this is just the expected value of this one plus the expected value of that one. And likewise for all of these. All of those expected values are just mu. So we can plug in mu now. Mu plus mu is 2 mu. This is, well, there's n of them minus the 2 that are missing. So that's n minus 2 lots of mu. Maybe be more clear than that since this is a show that question, but I think I get away with that. This cancels with this. We end up with just mu, of course. So that's good. We've done part A. B is finding the variance of these two things. Of course, the reason we're going to do this is because if both estimators are unbiased, they're sort of both as good as each other because they're both unbiased. But if one of them has a larger variance than the other, that will mean it's a worse estimator. You want smaller variances if they both have the same level of bias. So, okay, let's work out the two variances then. We just need to be careful here because variances, of course, behave a little bit weirdly sometimes. But that's okay. So we've got k as this again. The variance of k is, of course, the variance of that. Like I said, when we bring out this constant here, that's not just going to come out to the front as it is. It's going to square because it's a constant. And when you bring constants out from the inside of when you've got a constant multiplying some statistic like this, you bring it out and you square it. So okay, we've done that, and now we've got all this to deal with. So again, we can split these variances out into all their separate bits. But again, we've got more constants here, so when they come out, we're going to square them all as they come out. So we're going to end up with this here. And this is very good. We know the variance is sigma squared, so we can replace all of these with sigma squareds, and we end up with this. We can factorize out the sigma squared to get this, and now we've just got a sum of squares to do. And we can break out the formula book one more time here, and we'll find this from, I think, regular. Is it core pure? This is in, I think this is in core pure. So we find it in the formula book. We can replace that with this here. It goes up to n, so it's just this formula right here. Some stuff cancels here. This goes to a 2/3, I guess, and we end up with this, and that'll be the variance of k. So we'll park that for a second, and we'll work out the variance of L, which is actually slightly easier because this is the slightly easier one to use. Again, we can break these up into variance of this, variance of that. When we bring out that third, we're going to have to square that because, again, it's the same reason as we squared it before. It's just a constant. Bring out that and square it as well. Of course, the variance of this is just the two variances added together, and likewise over here, which is just sigma squared plus sigma squared into lots of sigma squareds. In fact, n minus 2 of them, as we saw before. There's up to n, but you're missing the first two, so that's n minus 2 lots of them. And again, we're going to do a little bit of collecting together here. This is 1/9 times 2, which is 2/9. This is obviously a 9th there, and this is one of these cancels one of those. We can bring those two things together by timesing this by n minus 2 of n minus 2. And we have 2n minus 4 plus 1, which is 2n minus 3 lots of them, and we get this here. So those would be our two variances. And it says the winner is the person who finds the better estimator. Now, these aren't clear which one is less than the other one. But when n is very large, what happens to this one when n is very large? Well, there's a quadratic value or term of n on the bottom here, and only a linear one on top. So when n is very large, when it goes to infinity, this entire thing just tends to 0. So that's very good. It's very good that the variance goes to 0 as n becomes very, very large because of that quadratic term, just massively outdoing anything that's on the top here. Now this one, when n goes to infinity, you can ignore these constants here. These n's just cancel and you get 2/9 times sigma squared, which isn't 0. It doesn't tend to 0. It gets locked somewhere down here. And so this one, when n is very large, tends to something lower than this one does. And so k is the better estimator. And this guy wins here because his is lower. That's not necessarily true for smaller values of n. There could be some values where this is the smaller one. But for large values of n, this guy does win. Good. So yeah, a couple of really nice questions to finish here. We've got a continuous uniform distribution between 4 and 10. So that looks like this, of course. This height here will be, well, we need this entire area to be 1, don't we? So it needs to be, this is 6 across, so we need a 1/6 to make it area 1. Doesn't end up mattering too much, I don't think, but the probability of any value L here is just going to be a 6th, and that's what we'll have there. And now, okay, so let's think about what we're actually doing here. We've got a rectangle with area 40, and we already know the length of it needs to be L. So we've got the height here, I'll just call it H. We know that H times L needs to be 40, which means that H needs to be 40 over L, we can say. And now we're doing something about the perimeter. Well, the perimeter is just 2L plus 2H. But H is 40 over L, so 2H is 80 over L. And we end up with this expression for the perimeter. And we're thinking about the expected value of this perimeter here. So look in the formula book, something quite useful up here. So the expected value of the perimeter, that's this. In the formula book, it tells you how to work out the expected value of a function of x. This is a function of the thing that we've got here, L, the original thing that we were looking at. And that's the integral of g of x, which would be this function here, times f of x. Now, f of x is just 1/6, right? Because this original function, this is just the line y equals a sixth, isn't it? The function is just y equals a sixth. So that's f of L. And so what we can do to work out this expected value is just integrate this thing here times by a sixth, dl, of course, between 4 and 10, because those are the two limits that this probability distribution exists over. And I think this is all we have to do. And this really isn't too hard from here. Factorize out 2, factorize out a sixth, 2/6 is 1/3. Do some integrating. I'll spare you too many details here. This doesn't end up being too difficult. I'm just trying to squeeze it into the space that I've got here. This is what, 50, and this is 8, so that makes 42. This, take away this, you can do 10 divided by 4 is 2.5, just following log laws. You can just type that into a calculator and you get this here, and that'll be our answer. Final question then, question number 8, really nice question about cumulative distribution functions. So here's the one they've given us between 1 and 3. It says find the exact value of the median. Now the median, of course, is where half the data is below it, half is above. So you could literally just do f of m, if m is the median, equals 0.5, because that's what the cumulative distribution function means, right? It cumulatively gets to the place where that amount of data is below it. So f of m is just 0.5. Or you could set up something like this. You could kind of think it through and say, well, if you differentiate this to get the probability density function, you would then have to integrate that between the start and the median to get half your values, just thinking about areas. But of course, integrating something you differentiate just gets you back to this, and then you sub in the m and the 1, and we get here. But of course, when you sub in 1, you just get to 0, and so this all just goes away anyway, and you just get this statement, which is just f of m equals 0.5, essentially. So we're just back to here. Anyway, we can solve this in a calculator, of course, after we do some tidying up. We get this. 3 plus root 2 is bigger than 3, so that can't be right. So the median has to be 3 minus root 2. For this one here, we can use this idea here, which I pasted. Probability of B given A is P of B, A and B over probability of A. So probability of A is just being between 1.2 and 3. So we can just substitute those two values into the cumulative function. And probability of A and B is being between 1.6 and 1.2. So we can sub in those. You can probably, I think, just type that into an advanced calculator nowadays. Essentially, you end up with this idea, right? You put in 1.6, you put in 1.2, you put in 3, but when you put in 3, you just get 1 based on this definition here. You put in 1.2. You can definitely put that in a calculator if you just have the function in there. In any case, however you're doing this, this will be the answer here, and you'll get it done. Now, this is the toughest bit of the paper, I think. The random variable y is 1 over x. So let's think this through really carefully. Now, remember, I mean, it's literally the first thing the textbook tells you about cumulative distribution functions, is that the f of x, the big F of x, is just equal to the probability of x being less than that number there of x. I know there's lots of x's going on here, so that's confusing. But this is the definition of the cumulative distribution function that's given to you in the textbook. This is what I was saying earlier about you could just put m in here, and the probability of being less than the median is a half. So this is why this first bit was just f of m equals a half, just based on this definition. So, okay, what can we do with this? Well, I mean, we can just put y in for a start. If we've got some cumulative distribution function y, that's going to be our definition here. Except y itself, big Y, is 1 over x. Let's put that in there. And now I can multiply across x and divide by y, and we end up with this. And now this is quite interesting, because what I'm going to do with it is I'm going to obviously say that I can then rewrite this in a more normal way, which is just to put the greater than symbol here instead. But like, what's the probability that you're greater or equal to this thing? Well, isn't it not the same as 1 minus the probability of being less than? I think that's pretty nice. I can just do that. But then look at this really carefully. Probability of x being less than or equal to 1 over y, well, just based on the definition of a cumulative distribution function, if you just replace that with a 1 over y, that's 1 over y. So this is just big F of 1 over y. And we've made some real progress here, I think. I think this is going to do us really nicely, because all we have to do is sub in 1 over y into this thing here. and which will give us just 1 over y's here, and we can also put 1 over y's here. And now there's a fair bit of tidying up to do, particularly on these limits over here. So what I'm going to do is if I times that by y, this is going to flip over, so it's going to be 1 here and y there. If you times that by, well, I don't think I times by y here. I think I just changed that I flipped all of these over. I found their inverses, so this became a 1 over 1, this became a y, this became a 1 over 3, and then I flipped those signs just because that's what you do when you do the inverses like that. And then this last one here, I think I just kept the same apparently. So that's cool. I just kept it. No, I didn't. Sorry. I times by y divided by 3, and I end up with this. Now, we don't actually want that. We want 1 minus that for our functions. Let's do 1 minus that. So 1 minus this. So do it in thirds. 1 minus 0 is 1. 1 minus all of this is just this. So 1 minus this, minus makes it plus. Minus makes it plus as well. And then 1 minus 1 is 0. And I've also fixed up these limits just a little bit. I've said that this is just the same as y greater than 1, obviously. This I've written in the more normal way, and this I've also written in the more normal way as well. We can simplify that up a little bit, and the final thing I'm going to do is I'm just going to write that line first and that line last, just because, again, that's the more normal way of doing cumulative distribution functions. I think we end up with this answer, which ends up being correct. So that was the toughest thing about this. The last thing, hence or otherwise find the mode. I thought this was harsh because I think it's quite difficult to do that without getting this bit right. So these marks are very much tied together. But now that we've got this, so okay, we can differentiate that just to find the probability function. So I've just differentiated this. This is, of course, y to the minus 1, which makes this whole thing y to the minus 2. Minus 2 comes down to here, and then you lower it down to a minus 3. Same thing here. This is y to the minus 1. Multiplies down here, makes a positive, and then it becomes a y minus 2. This is a constant, so it goes away. And now the mode is when you have like a density function like this, the mode is the bit where it's highest up, right? Where the most stuff is right here. And of course, that's where the function's derivative is 0, when it's nice and flat. So if we find the derivative of this, again, just doing some normal differentiating things, we want this to be 0. We want a stationary point. We can times by y cubed, and we'll get this. We can add 3, we can divide by 1.5, and then we can take the minus 1th root of 2, and we'll end up with a half. And that will be the mode. And thank you so much for watching, and I'll see you next time.